Where is all the carbon gone? Carbon, life, and energy are tightly intertwined. Photosynthesis uses energy from the sun to convert inorganic air into living biomass. It's amazing. The photosynthesis involves little carbon atoms being taken out of the air, dead air, strung together like beads on a string with energy captured from the sun. This is where all living biomass comes from. It's a conversion from non-living into living material. Almost all of the carbon that's fixed this way is turned back into CO2, virtually every last atom. And that's when plants are eaten, typically by bacteria or other microbes, or also when animals eat the plants and then bacteria eat the animals. About 1/7 of all the CO2 in the atmosphere is converted to plants every single year. So left to its own devices, this would eliminate all CO2 in the atmosphere in 7 years. Luckily, that's not the case because that would be the end of the world. And in fact, that also means that 1/7 of all of the CO2 in the atmosphere is created every year through death and decomposition. So there's this fantastic, amazing, rapid cycling of carbon from the atmosphere through the biosphere every year. Back in the 1950s, Dave Keeling, who at that time was a young man, developed an instrument that could precisely measure CO2 for the very first time. He began measuring CO2 in Southern California in 1957, and in 1959, the year I was born, put instruments at the top of a huge mountain in Hawaii in the middle of the Pacific, 13,700 feet, and began measuring CO2 continuously. It has been measured every hour of every day since then for a very long time. And by the middle of the 1960s, Keeling and other people looking at those data were able to show that CO2 was rising quickly, not dissolving entirely into the oceans as previously thought. So burning fossil fuel was increasing the atmospheric concentration of CO2. They also showed this incredible seasonal cycle of northern summertime drawdown of CO2 and then recovery of CO2 or increase in CO2 during the northern winter. And they were able to show that the increase in the atmosphere is only half the rate at which CO2 is being produced by burning coal, oil, and gas. So easy to find out how much coal, oil, and gas are being burned. You just basically ask the oil and coal companies how much fuel they produced that year. And easy to compare that to the amount of increase in the atmosphere. And they were able to show that in fact, half of the fossil CO2 was missing. So we knew that the rate at which we're burning stuff is twice the rate at which the air is accumulating the residual. So when I was a little kid, the US and the Soviet Union did a terrible thing. They used to blow off nuclear weapons in the atmosphere to test them. And it was a scary thing. It was a bad thing, but something good came out of it. In 1963, the US and the Soviet Union decided that they wouldn't do this anymore. They signed a comprehensive nuclear test ban treaty that promised that when the treaty went into effect, they would stop blowing off nukes in the atmosphere. So of course, before it went into effect, they blew off dozens of nuclear weapons, all in pretty much early 1964. So dozens of bomb tests quick before the treaty went into effect. As a result, there was this huge spike of radioactive radiocarbon CO2, C14O2, which is produced in other ways, but because of the bomb testing, there was this huge slug that came out in 1964. Now, the radioactive CO2 behaves just like any other CO2 in terms of like photosynthesis, the plants take it up, in terms of the chemistry in the oceans can dissolve the CO2 into the surface oceans. But unlike all the other CO2, it was labeled. It was like, had little labels on the forehead of each one of those little molecules that says, I was made in 1964. And by tracing the made in 1964 radiocarbon CO2, oceanographers were able to go out and find all of this radiocarbon in the ocean. Kind of amazing. And they discovered by around 1970 that only half of the missing carbon was in the ocean. So remember, half of the CO2 from fossil fuel stays in the air and the other half doesn't. And then by tracing the radioactive bomb pulse in the 60s and early 70s, oceanographers were able to say that they could only account for half of the missing CO2. So that led to this concept of the missing sink. So if you imagine commercial records, you ask Exxon and Peabody Coal how much carbon that they dug up last year, and we call that 100%. The increase in the atmosphere is about 50% of that. So that's direct measurement. You can just sort of measure the changes in the atmosphere from year to year. Then on the other hand, the bomb C14 showed that oceans were taking up about 25% of the total fossil fuel emissions. And that left you with this missing sink of about 25% of fossil fuel emissions, just as a residual, right? You add up, fossil fuel minus atmosphere minus ocean, and you're left with this missing sink of about 25% of fossil fuel. So oceanographers discovered this. And so they published a bunch of papers that said, well, the land must be taking up the CO2. Kind of makes sense, right? Where else is there? There's the air, there's the oceans. What else is there on Earth? There's the land. So the oceanographers just sort of posited, hypothesized that extra CO2 in the atmosphere was leading to extra photosynthesis, right? Since plants eat CO2 for a living, if you give them more CO2, they're going to bulk up. So I call it like the Girl Scout cookies theory of dieting, right? If there are Girl Scout cookies in my house, my biomass increases over time. The idea is that adding CO2, plant food, to the atmosphere makes plants get heavier over time, and kind of stands to reason. But if you think about it, that's not really enough. So let me take you through the logic here. Adding CO2 does in fact make plants bulk up. We know this because we can do it in the lab, right? We can do this in a greenhouse. You take plants and you grow some of them in ambient CO2 and some of them in higher CO2. And this is a particular experiment that's published about 15 years ago that shows rice, identical rice grown in different levels of CO2. And you can see that the higher the level of CO2, the sort of faster the rice grows. And so you think, well, the oceanographers are right? This is a Girl Scout cookies theory. The more CO2 there is in the atmosphere, the bigger the plants get. That must be where a quarter of all the fossil fuel CO2 is going. But that neglects the fact that stuff dies, right? All things die, even plants. So eventually, just having more plants doesn't mean you have less CO2, because eventually every atom of carbon that goes into those plants comes back out as a molecule of CO2 when bacteria or fungus or whatever eat that plant material and respire the CO2 back to the atmosphere. So you don't necessarily get a net uptake of carbon just by having a net increase in photosynthesis. You have to have plants growing faster than they're dying. It's not enough to just have plants growing more. They have to continually grow more, even though there's more dead plants around, which should produce more CO2. However, we know from looking at ice cores that for a long time before the Industrial Revolution, the amount of CO2 was not going up or down over time. That to a pretty good approximation, the CO2 was dead steady over many centuries, even millennia, before the Industrial Revolution. So it was about 280 parts per million of CO2 in the atmosphere for a very long time. And only around the year 1800, when fossil fuel extraction and combustion first really took off, did the CO2 start to increase. So we know that at least over very long periods of time, the amount of growth and death are pretty much balanced. And it kind of has to be so, right? You make more and more living stuff, and therefore there's more and more dead stuff. It's just sort of built into the logic of life. However, when we say that there's a carbon sink on land, we are saying that in my entire lifetime, since Keeling discovered this back in the 1960s, plants are in fact growing faster than they're dying. This is an amazing thing. Completely not what people expected back in the 1970s. We thought that, tropical deforestation, land clearing for agriculture, all that kind of stuff was destroying biomass at a phenomenal rate. And that here in the sort of 1970s and 80s, it became quite obvious by looking at data in the atmosphere and the oceans that in fact there has to be something that's causing plants to grow faster than they're dying worldwide. We know that since about 1960, at least, and actually before that, but we didn't have good measurements, growth minus decay, the imbalance between life and death, is something like 25% of the rate of fossil fuel combustion. So how is this possible? What about the fact that we're like wiping out forests left and right, that we're clearing land, that we're plowing the prairies and releasing carbon from the soils to grow crops and so forth? There's got to be something that accounts for the fact that growth is in fact faster than death. In fact, if you just sort of assume that that photosynthesis, that is gross primary production, or let's say net primary production, increases along with this this black line here with the CO2, then after some delay, there's an increase in decomposition, right? Because everything that grows has to die. And the time scale of that delay is something on the order of 20 years. Like, right? So some of the carbon in the biosphere only lasts for like a week, right? Like the blades of grass in my backyard before my dog digs them up. On the other hand, other molecules of organic carbon in the biosphere might last for 1,000 years, right? Like giant redwood trees or something like that. So the flux weighted average time of residence time of carbon in the biosphere averaged worldwide is some kind of average of all that stuff, give or take 10 or 20 years. But if there's a delay that's sideways on this graph, that means in any given year, the growth is faster than the decomposition. And so that's where you can get a net sink from the small difference between CO2-driven photosynthesis and CO2 production by decomposition. As long as the rate of, as long as CO2 is rising, the growth rate is greater than the death rate in any given year. So people have gone out in the field and studied this, not just in labs. It's incredibly difficult. You go out and you put a ring of towers out in the woods and you spray, gas CO2 over those rings, and as the wind shifts or blows faster or slower, you have to change the amount of CO2 coming out so that in the center of those rings, the amount of CO2 stays constant at a given level. And people do this for years and years, even decades. It's called free air carbon enrichment, or FACE. And you fumigate a particular ring with a particular level of CO2, and then you control for many replicates of it, and you control for different amounts of water, different amounts of nitrogen, different temperatures, and so forth. What these studies have tended to show is that you get a bump in NPP, the net primary production, for a few years in the elevated CO2 plots, but the ambient CO2 plots and the elevated CO2 plots tend to converge over time, over like a decade or so. And this has been interpreted as nutrient limitation. So the idea is that you give these plants an extra slug of CO2 and they grow faster, but pretty soon they don't have enough nitrogen or phosphorus or water or something. There's some other necessity in the ecosystem that limits their ability to take up the extra CO2. And in fact, you see studies like this where you have CO2 initial bump in the growth rate, and then it sort of peters out. And then if they take one of those rings and they give it a big slug of nitrogen, then you get another bump of growth for a while until it peters out and so forth. So this is like acclimatization to the amount of extra CO2, and it is set by the nutrient availability. But in fact, we're also giving plants extra nitrogen. It's not just CO2 that people are treating the world with. We are also fixing nitrogen. So the world is just awash in nitrogen, but it's almost entirely triply bonded N2, right? So two N atoms bound with 3 pairs of shared electrons. The air is 80% nitrogen, but it's chemically inert. It's biologically inert. That nitrogen doesn't do diddly squat for plants. Back in the day, almost all of the bioavailable nitrogen was produced by lightning or specialized microbes. But since about the early 20th century, using a process originally pioneered by Haber and Bosch, people have been fixing nitrogen like crazy. We compress air and heat it up using fossil fuels to extract reactive nitrogen out of the air. And we use that to make fertilizers. And that's where the Green Revolution comes from. And some of that fertilizer gets out and winds up fertilizing the biosphere as well. In addition, all by accident, we actually burn air in high pressure and temperature combustion, right? So in smokestacks or in your car where you're compressing the air 20 to 1 and like setting it on fire in your engine. Some of that N2 reacts with the O2 from the air and makes NO and NO2, and that is chemically reactive, and it goes out into the clouds and downwind and becomes like dilute miracle grow from the skies. In fact, you can trace sort of fossil fuel emissions and then the downwind transport of reactive nitrogen from the power plants or from the cars and factories, and the resulting uptake of that nitrogen by ecosystems. And in fact, forests are like 200 to 1 carbon to nitrogen. So every kilogram of nitrogen that you dump on a hectare of nitrogen-limited forest is going to result in 200 kilograms of carbon taken up. And in fact, this is happening all over the sort of middle latitudes of the Northern Hemisphere due to industrial combustion. Another thing that's an important part of this story is changes in land use. So we've already talked about how people are changing land use because we're cutting down forests and we're paving the paradise and putting up a parking lot and all that kind of stuff. But there's another side to changing land use. And I want to just mention that when I was a kid in New England, we would walk around in the woods and we'd see these amazing stone walls all over the place with like trees all up to them. Like, what the heck was somebody doing way out in the woods building these, beautiful stone walls that are all covered with lichen? And how come they put all that effort into building stone walls in the woods? Well, of course, the answer is they didn't used to be woods, right? This used to be a farmer's field. There was no forest whatsoever in New England in 1850. It was all farms and pastures across New England. But in the 20th century, all those farms went belly up. And essentially agriculture moved to the Midwest and California. And all those acres of former pasture and farmland have regrown into woodlands and forests. And so you could sort of think of like every molecule of wood in Vermont or Massachusetts was derived from a molecule of CO2, right? The CO2 has gone to build forests in these places that used to be farms. Another really important part of this story is boreal warming. So as you probably have heard, the Arctic is warming at something like 3 times the rate of the rest of the world. And many places in the Arctic and boreal forest now have 50% more frost-free days than they did 50 years ago. Kind of an incredible statistic, even just in and of itself. The growing season is getting much, much longer in the high latitudes, and that's where most of the land is. There's much more land up at the high latitudes than there is anywhere else in the world. And as those growing seasons get longer, you get woody plants sort of encroaching into what used to all be tundra. And all those woody plants store more carbon than the grasses and herbaceous plants that were there before. So this is actually a satellite-derived map of the change in plant growth in percent per decade. And you see these hotspots as you go way up in the north. So ironically, global warming is causing some carbon to be sequestered in the high latitudes. Now, of course, if you do that too much, you don't just get shrubs growing in the tundra, you might thaw the permafrost, and that's like an increase in decomposition. So these things don't necessarily last, but you can get a temporary increase in carbon storage from warming up the high latitudes. Now let's talk briefly about the oceans. The ocean's kind of a simpler story in some sense because it's just chemistry. So if you think about the chemistry of CO2 in water, CO2 dissolves in water to make something called carbonic acid. That is H2CO3. And H2CO3 is in chemical equilibrium with CO2 and also with bicarbonate ion and carbonate ion in the water. That's called carbonation. And this is the reason why beer goes good with pizza and Chardonnay goes good with brie. It's the carbonic acid that dissolves the fats on your tongue. It tickles your tongue with the little bubbles of CO2. It's good. And as we know, because we've experienced this in real life, CO2 dissolves better in cold water than it does in warm water, right? This is why beer or soda go flat. If you put the beer on the kitchen table for an hour or so, and it warms up, the CO2 comes out of solution, and it's no longer any good. And for this exact same chemical reason, cold polar ocean waters soak up CO2, and warm tropical ocean waters release CO2 back to the atmosphere. The CO2 dissolves in the high latitudes because the water is cold, becomes carbonated, make carbonic acid. It's actually bad for the oceans in the long run because carbonic acid is incompatible with a lot of biology, but it's good for getting CO2 out of the atmosphere. The other thing that's important to know about the oceans is that the oceans are not well mixed, okay? The oceans have layers. There's a warm surface layer that's in contact with the sun that winds up getting buoyant, right? As you warm the surface water, it floats. It's very buoyant relative to the water underneath, and it makes this kind of unmixable skin of warmth on top of the water, and the cold water sinks to the bottom. So the oceans are super deep. It's like 13,000 feet deep on the average, and that surface water seals off the water underneath so that it doesn't touch the air. The only way to get water to sink to the bottom of the ocean is to make it even colder than the bottom of the ocean, and that happens at the high latitudes of both hemispheres. So in the North Pole around January, it gets super cold up there. The South, Antarctica around July, gets super cold down there, and that water will then sink to the bottom, and it slowly fills up the entire ocean from the bottom up. It takes about 1,000 years for that to mix, but the middle part, this great big intermediate water part, is water that has not touched the air for 1,000 years, since like William the Conqueror. That water doesn't know we're here yet. That water has no dissolved CO2 in it. In fact, people have gone out and mapped this incredible amount of effort to go across the entire oceans, and you can count the number of anthropogenic CO2 molecules in the water as a function of depth in the Atlantic, the Indian Ocean, the Pacific, and you can see that the stratified water holds almost all of the anthropogenic CO2, the fossil CO2, right at the top, and it can't mix down. So the rate at which the oceans can take fossil CO2 out of the atmosphere is limited by the rate of physical mixing between the warm surface water and the cold water at depth. The whole thing is kind of like a giant titration, right? Did you do titrations when you're in chemistry class, where you drip acid beep, 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 into a beaker of water and you measure the changes in pH? That's what we're doing to the oceans, very slowly putting carbonic acid into the oceans and allowing them to mix over thousands of years, changing the pH of the oceans, changing the chemistry of the oceans. So where has all the carbon gone? In a nutshell, both dissolving into the oceans and also a very slow but steady removal of biological CO2 from the surface of the oceans. You make phytoplankton and they get eaten by zooplankton, and some of those get eaten by fishes, and some of those come out as fish poop, and a little tiny bit of that can sink down into the deep ocean and then decompose down there. So that's called the biological pump. On the other hand, on land, we've got CO2 fertilization. The plants are eating CO2. Maybe that makes them grow faster, but then of course they also die, so you have to account for that. Part of the extra growth is due to nitrogen deposition and other kinds of fertilizers. Part of it is due to the regrowing of high carbon landscapes like forests in places that used to be pastures and farms. But then there's also other kinds of land use that sort of counteract that. And finally, the response to the global warming, especially in the boreal forest and Arctic, with the longer growing season, we're able to grow more carbon dense landscapes up there. So the trouble is these sinks, these processes that take CO2 out of the atmosphere slowly saturate over time. So on the land is very vulnerable. If you think about it, only CO2 fertilization really has legs. You give extra nitrogen to a plant and it will take that up and it will grow more, but just giving it 10 times more Miracle-Gro isn't going to make it grow 10 times faster, right? You're going to, at some point, exceed the nitrogen demand of an ecosystem, at which point it's going to seep out the bottom or even be detrimental to the plants. Also regrowth, right? So there's a regrowing forests in New England. Once they're done regrowing, then they're no longer growing faster than they're dying. They're just dying as fast as they're growing, and you no longer have a sink. Boreal warming is even worse, because a little bit of boreal warming and you get shrubs in the tundra, but a lot of boreal warming and you might wind up thawing the permafrost and then switch the Arctic from a sink to a huge source. In the ocean, probably a safe place to put the carbon for the near term, because it's hugely deep, and that big black blob of cold water at depth isn't going to come back for a long, long time, like 1,000 years. But on the other hand, as the water warms up at the surface, it's harder and harder to get it to mix down and carry that water to depth. And in fact, even then, once you get it at depth, at some point, the acidification of the water limits the total amount that you can dissolve in there. So even the oceans in the long run are a not infinite reservoir for the CO2. In fact, you've almost never seen graphs like this that go out for 40,000 years. That's kind of ridiculous. But this is a study that looked at the ultimate fate of anthropogenic CO2 in the atmospheric system. Some fraction, like 60%, resides in the atmosphere at the time when fossil fuel burning ends. And for the next several millennia, that extra CO2 after fossil fuel winds up dissolving into the oceans until you've saturated the chemistry of the oceans. And that takes on the order of 3 turns of the ocean cycle, let's take to the year 5000 AD. At that point, you have reactions with calcium carbonate in the ocean that can buffer the carbonic acid that's coming in from the atmosphere. At some point, you even consume that buffering capacity out in the sort of 20,000 year AD time frame, and then you're left with some slug of CO2 in the atmosphere that isn't going to go away for geologic time. You have to wind up dissolving igneous rocks on land to get rid of that CO2. It's going to take tens of millennia to get rid of that CO2. So I want you to remember from all this, one, carbon cycles vigorously between land, oceans, and air. About 1/7 of all the CO2 goes into the biosphere every year. About 1/7 of all the CO2 in the atmosphere comes out of the biosphere every year. It's a very, very vigorous cycle. About half of all the CO2 from fossil fuels stays in the air. And the missing half, the half that's not in the air, is divided roughly equally between land and oceans. The land photosynthesis, believe it or not, exceeds respiration, exceeds decomposition by about 2% each year due to CO2 and nutrient fertilization, due to regrowth, due to boreal warming. This is the land sink. And it's only about 2% of photosynthesis, but it's about 25% of fossil fuel emissions. Amazing. However, unfortunately, much of that fossil CO2 will remain in the air for many, many millennia after people are all done burning coal, oil, and gas.